Hi, my name is Noor. I'm the main programmer of Team LazyGo, and we are participating in the Future Engineers category of World Robot Olympiad 2025. At first, I want to talk a little bit about our control system. So we are using robot operating system as the backbone of our whole control system. So we are using ROS2 because ROS2 actually allows you to divide a big problem into smaller categories. For example, we have to handle the sensor values, we have to control the actuators, we have to actually detect the towers, the individual towers. So what we do is all of these problems are actually handled by separate nodes in ROS2, and they all communicate between each other, which makes the job really easy. So for basic obstacle avoidance, we are actually using disparity check algorithm, which is a modified version of follow the gap algorithm. So what it does is it actually throws around a bunch of circles, and whichever circles actually moves to the furthest distance, it targets that circle, and that is its target angle. So it has a few drawbacks. For example, it actually has a tendency to move to the corners of the tracks, but we actually solved that problem. So now it's actually working really fine for us. To detect the traffic towers, normally you'd use a color matching system using the camera, but there are some problems with that. For example, a lot of times the camera actually detects the parking spot as red towers because their colors are very similar. So what we did is we actually used the LiDAR values to actually match the shape of a tower. So we can detect the towers using the LiDAR values, and then we use the camera to detect its color. So we don't have the problem that the LiDAR is actually detecting the tower as a traffic space, or it's detecting the traffic space as a tower. That's not happening for us because their shape is different, and using LiDAR we can detect those shapes. Okay. A very interesting thing in our robot is actually we are calculating its real-time position in the track. So we are actually fusing the encoder value and the IMU value together, and thus we can actually determine the exact position with centimeter accuracy in the track of our robot, which really helps us with parking and obstacle avoidance and a lap count. Due to academic reasons, I had to stay away from my team for a few months. So I did not have access to the physical robot of our team, which made it very difficult for me to write software for our robot. So what I did was, during that time, I set up a simulated world in Gazebo. By the way, Gazebo is a robot simulator. If you have a 3D representation of your robot, then you can simulate it there. Fortunately, Gazebo has really good compatibility with ROS2, and I did all my logics on the simulated robot, and when I came back to my team, I implemented those logics on our actual physical robot, and it worked just fine. And all the simulated files and necessary scripts, those can be found in our GitHub repository.
Hello everyone, my name is Prithul and I'm mostly handling the electronics on our robot. In the electronics, we had to make sure nothing comes loose while the robot is moving and that the entire system remains reliable during testing and iterating our code. The main components of the electronic side of things include a Raspberry Pi running ROS2, an ESP32 microcontroller, and a robust power distribution system that delivers clean and stable power to all our devices. Since high-quality SMD PCB manufacturing isn't easily available in Bangladesh, our goal was to use only off-the-shelf and through-hole components that we could source locally. This allowed us to design and assemble our own PCBs at home, which means we could rapidly iterate our designs. The robot gets power from a 3-cell LiPo battery connected via XT60 connector and a main power switch. To keep things clean and noise-free, a dedicated 5-volt converter powers the Raspberry Pi, the ESP32, and encoders, isolating them from the motor noise. A separate 5-volt 5-amp buck converter powers the servos, infrared LEDs, buzzer, and a few other components. The ESP32 monitors the battery voltage and warns us when the battery is running low. The main PCB was designed in EasyEDA. Almost all our components are on the top side for easy assembly and access, except for the 5-volt 5-amp buck converter, FTDI programmer, and a few SMD MOSFETs, which are at the bottom. We learned from our earlier versions that noise was a big problem, especially from the servos. So this revision is packed with decoupling capacitors all over the board to keep power clean and stable, not all of which are populated. On the schematic, nearly every pin of the ESP32 is used. Up top, you'll see the buck converter, indicator LEDs, and basically all our input and outputs are neatly organized. A MOSFET allows us to turn the IR LEDs off when needed. So that's the electronic systems behind our LazyBot. Reliable, locally sourced, and built for fast iteration.
Our robot is entirely custom-made and mostly 3D printed. First, we designed the robot in Onshape and finalized all the details. Then we 3D printed the base, the steering mechanism, which you can see here in action, the motor mount, and all the other parts. A huge thanks to bot engineers for printing these beautiful multicolor parts. Well, this can also be printed in single color. Anyways, we are using Ackermann steering system and differential gear system for our robot, which allows it to take really tight turns. Now, this was the turning radius of our robot previously, and this is how it works now. Let's see how we assemble all the parts.
Thanks for watching.